previously, when we looked at sequences, we guessed at the limit of a sequence by looking at the behavior of the terms as n gets larger. So basically, we guessed at the value of the limit. So in this video, we're going to look at other techniques for calculating limits of sequences. So the first idea is that you can think of sequences as functions. We think of sequences as functions, and then we can use all the previous techniques we had for functions, such as L'Hopital's rule. Okay, so let's look at a few examples. So suppose I have the limit as n goes to infinity of 3n squared minus n over 4n cubed plus 2n squared. Okay, so we think of this expression as a function. So if we look at what happens when n goes to infinity, this is infinity over infinity. So if this were a function, we would use L'Hopital's rule. So then we take the derivative of the top and the bottom. The derivative of the top is 6n minus 1. The derivative of the bottom is 12n squared plus 4n. Then as n goes to infinity, this is still infinity over infinity. So we again use L'Hopital's rule. So the derivative of the top is 6. The derivative of the denominator is 24n plus 4. Now, as n goes to infinity, the numerator is just 6, and the denominator goes to infinity. And so this goes to 0, because the denominator gets larger and larger, so the whole fraction gets smaller and goes to 0. Okay, so that's the first example. So let's take a look at another limit. So the limit as n goes to infinity of cosecant inverse of n. Okay, so for the inverse trig functions, we have the following identity. So we have so cosecant is related to sine, so they're inverse functions. It is related by the following property. So the inverse cosecant of n is the same as inverse sine of 1 over n. So let's rewrite this limit using sine inverse. And then as n goes to infinity, 1 over n goes to 0. So this just goes to 0. So this is the inverse sine of 0. The inverse sine of 0 is equal to 0. So this limit is also equal to 0. Finally, let's take a look at one last example. So the limit as n goes to infinity of 1 plus 2 over n to the n. Okay, so as n goes to infinity, inside the parentheses this goes to 1, and the exponent goes to infinity, so this is of the form 1 to the infinity, which is an indeterminate form. And so this kind of indeterminate form The way to do it is to take the natural log first and then use L'Hopital's rule. Okay, so then we take the natural log. The limit becomes, the limit as n goes to infinity, so the exponent comes down, times the natural log of 1 plus 2 over n. And then I rewrite this limit as a fraction. So the limit as n goes to infinity, the natural log of 1 plus 2 over n over 1 over n. And so now this is 0 over 0, which now we can apply L'Hopital's. Says this is equal to the limit as n goes to infinity. So the derivative of the top is 1 over 1 plus 2 over n, and then using the chain rule, the derivative of 1 plus 2 over n is minus 2 over n squared. And then in the denominator, the derivative of 1 over n is minus 1 over n squared. So this n squared cancels out this n squared. And so this is the limit as n goes to infinity. So let's rewrite this. So the minus 2 and the minus 1 becomes 2, 1 plus 2 over n. So now as n goes to infinity, this goes to 0. So we're left with 2 over 1. And so the limit is, this limit is 2. So we're actually not quite done yet. So in the beginning we took the natural log, so we have to exponentiate to get back the original limit. So the limit as n goes to infinity of 1 plus 2 over n to the n would be e to the 2. Okay, so these are some examples of computing limits like if they were functions. So let's see a few other techniques that there are for limits. So for a special kind of sequence called a geometric sequence, so geometric sequences are of the form r to the n, where r is a fixed number. So r is called the ratio. So for these kinds of sequences, there's a simple rule for calculating the limits depending on what the ratio is. So the limit is equal to 0 if the ratio is between minus 1 and 1. It's equal to 1 if r is equal to 1. Because if r was equal to 1, then this whole thing is just equal to 1. If r was between minus 1 and 1, so r would be a fractional value. And then as n gets bigger and bigger, what we're doing is we're repeatedly multiplying by r. And because r is a fractional value, repeated multiplication by r will make the number smaller and smaller. So as n goes to infinity, the number will get smaller and smaller until it goes to 0. So that's why this is equal to 0. And finally, if r is less than or equal to minus 1 or bigger than 1, so now we have a value that's bigger than, say if r was bigger than 1, then repeated multiplication will make the number bigger and bigger, and then it will go to infinity. If r was less than or equal to minus 1, then it's a negative large value. It'll alternate between negative and positive, but then the value will still get bigger and bigger. So this doesn't exist. So for example, limit as n goes to infinity of 2/3 to the n. So here 2/3 is between 1 and 1, and so r is equal to 0. So in this case r is equal to 2/3, which is between 1 minus 1 and 1, so the limit is equal to 0. Limit as n goes to infinity of, say, minus 1.2 to the n. So here r is equal to minus 1.2, which is less than negative 1, and so this limit doesn't exist. So for geometric sequences, all you have to determine is the value of r, and then following this rule you can know what the limit is. Finally, another method of computing sequences is called the squeeze theorem. And this is useful for sequences that oscillate or alternate. Okay, so the idea is the following. So suppose the limit as n goes to infinity of some sequence is hard to compute directly. So the idea behind the squeeze theorem is that if you have a limit that's hard to compute directly, so again, most of the times it'll be an oscillating or alternating sequence, then what we do is we find two other sequences, let's call them an and cn, such that the original sequence bn is in between the other two sequences for all values of n bigger than some index, and also if an and cn have the same limit, then the middle one, because it's squeezed between them, also has to have the same limit. So that's the idea behind the squeeze theorem. So let's look at some examples. So let's take a look at the limit as n goes to infinity of sine of n over n. Okay, so we know that the sine function oscillates. So let's try squeezing them between two other sequences. So we're going to use the fact that the sine function is always between 1 and 1. And so I can relate this to the sequence. So if I divide everything by n, so divide everything by n, so you get minus 1 over n is less than or equal to sine of n over n, which is less than or equal to 1 over n. So now our original sequence, so this is original sequence bn, is squeezed between these two other sequences, an and cn. So now what we do is we calculate the outside limits. The limit as n goes to infinity of minus 1 over n. So as n goes to infinity, this is 1 over infinity, which is 0. And then also limit as n goes to infinity of 1 over n. This is also 0. So this is exactly the situation in the squeeze theorem. So we have to have that the middle limit has to also be 0. So this is an example of an oscillating sequence that converges. Let's take a look at another example. So suppose we want to take the limit as n goes to infinity of minus 1 n plus 1 over n squared minus n. Okay, so now this is an alternating sequence. So let's try using the squeeze theorem again. So we have our original sequence. So we need to squeeze it between two other sequences. So the numerator changes between minus 1 and 1, right? So so when it's positive 1, it's going to be this sequence, and when it's negative 1, it's going to be this sequence. So we're going to use these two sequences for the squeeze theorem. So now the limit as n goes to infinity of minus 1 over n squared minus n. So again, the denominator gets bigger and bigger, so this goes to 0. And also the limit as n goes to infinity, 1 over n squared minus n. This is also equal to 0. So again, both the outside limits are 0, so the middle one has to be 0 also. So this is an example of an alternating sequence that converges. Okay, so these are some various different techniques to calculate limits of sequences. So finally, we're going to discuss some terminology. Of sequences. So the first is that of a non-decreasing sequence. A non-decreasing sequence is one where each term is greater than or equal to the previous term. So an plus 1 is greater than or equal to an. The next kind of sequence is a non-increasing sequence. So a non-increasing sequence is where each term is less than or equal to the previous term. So where an plus 1 is less than or equal to an. And if you have a non-decreasing or non-increasing sequence, the sequence is called monotonic. And finally, the last term is a bounded sequence. So a bounded sequence is one where if you take the absolute value of the sequence, less than or equal to some fixed number m, and all the terms. This is true for all the terms. So the reason that these terms are important is that there's a theorem that says that any bounded monotonic sequence is convergent. So an example is in a geometric sequence, right? So for example, an is equal to 1 over 2 to the n. So here, the sequence is the sequence 1/2. The n equals 1 is you have 1/2, 1/4, 1/8, 1/16, and so on. So this sequence is non-increasing. And also you can see that all the terms are smaller than 1. So 1 over 2 to the n, this is always smaller than 1. So it's bounded. And so in this example, this is a monotonic bounded sequence.